My presentation title is the first principles study on hydrogen atom interaction with BBC metals. For example, still hydrogen environment of fracture assistance and hydrogen leakage, hydrogen storage explosion, hydrogen induced cracking. Hydrogen embodiment in materials is one of the most important issues affecting the rapidly developing field of hydrogen storage. The current understanding for hydrogen experiment is that hydrogen in the environment dissolves into the steel and migrates and accumulates towards areas of steel stress construction. For example, crack tips, environmentally assessing crack nucleation and extension into failure. While these are helpful for understanding of hydrogen traps at both the microscopic and macroscopic cells. A precise physics of the interaction between hydrogen heterogeneous elements in steel is not yet fully illustrated. Therefore, in this work, a first principle study was carried out to understand the mechanisms of hydrogen diffusion and the interaction between the heterogeneous atom in steel at atomic and electric levels. And the second part is modeling and calculation. Hydrogen atoms were added to the models to the interstitial atoms, while the area atom in the center of the model was replaced by the carbon, silicon, magnesium, chromium, molybdenum, respectively, and the hydrogen in a pure area lattice. The energy levels of the hydrogen atoms after solute solution. Solid solution are distributed between -2 and -10 eV. There is only one wave peak for the hydrogen atom located in the -0.5 to 0.5 even rate before solute solution. While after solid solutions, the energy level splits and moves to the -8 to -10 even range. So, and the peak is significantly low. The aero atom is nearly the Fermi energy level with a contribution from the main 3D operators. In addition, the 1s orbitals of hydrogen and the 4s orbital of aero overlap in the -10 and to -8 eV range after solute solution, indicating a slight hybridization conjunction effect between aero and hydrogen atoms. And the hydrogen in aero X crystals. It is observed that the absolute value of the binding energy is low when carbon and silicon atoms are doped with that in pure aero crystals, indicate that the hydrogen solid solution in aero crystals doped with carbon and silicon can significantly reduce the atomic bodies of the aero. Furthermore, the wave peak of the hydrogen atom after solid solution is high when the hydrogen atom is located at site 1, then at both sites 2 and 3, reaching about 2.1 eV. This indicates that the electric density of the hydrogen atom is greater when the hydrogen atom is located at site 1, which in turn indicates that the more electrons the hydrogen atom receives from the aero atom, and the more stable the chemical bond is formed at site 1. This provides a new evidence for the preferential occupation of tetrahedral sites by hydrogen atoms. And hydrogen in aero crystals, the distribution of hydrogen chromium molecule around the Fermi energy level is dominated by the contribution of electric in the d orbitals, while the density of states in the d and p orbitals, this three atom receives little influence from solid solution hydrogen. However, solid solution of hydrogen affects the s orbitals of the three atoms in the -10 to -8 EV range, and the wave peaks in this region fluctuate depending on the size of the hydrogen atoms. This suggests that the aero chromium and aero molecule system has low energy impurity set induced from the dropped metal X from doping with chromium and multiple atoms compared to pure aero crystals. And the charge difference, densities, the site occupied by the hydrogen atom in the metal is determined by the competition between the two energies and the deformation energy. There may be some chemical bonding between the hydrogen atom and the metal atom to minimize the energy of the system. The electric structure of the aero crystal is lighted by the dropping of chromium and molecule atoms. The dropping with chromium atoms increase the number of the electrons gained by hydrogen atoms by about 87%. The dropping of the modular atom increase the electric gain of the hydrogen atom by only about 0.3%. This indicates that the different atoms dropping has also has varied effects on the formation of chemical bonds in aero crystals where hydrogen atoms are solid solute. And that this difference is significant. This also shows that for chromium and molybdenum dropped the aero crystals, the hydrogen atoms received more electric, and that carried mobility is greater in chromium and molecular dropped aero crystals than in pure aero crystals. This explains the greater susceptibility of high strength steels to hydrogen environment from atomic and electric point of view. And The alloy system dropped with Chromi and Mobidium significant change the electric closed density distribution of aero after solid solution of the hydrogen. The hydrogen atoms in rate gain electrons and Arrow, Corimier, and Molecular Autumn in blue, Lois electrons. Such forming ionic bonds, the light blue uniform electron could density distribution represents the metabolic bonding between the increased interacting atoms as the observer. And the obverse red-blue interaction between the Cora molecule and arrow represents the covalent bonding between them. And the stability of the arrow crystal has been changed due to the conflict effect of the metallic covalent and ionic bonding. And as the conclusions is hydrogen effect in steel was affected differently by different atomic dropping elements. Dropping with carbon, silicon, and molecular made solid solution of hydrogen in aero crystals easier, while dropping with manganese and chromium was rather more difficult. The second is the but the energy in chromium and molecular crystal varied with hydrogen atoms location, as the hydrogen atoms was able to reduce the repulsive forces between the aero atoms when they was in tertiary gap, which significantly reduced the by the energy of the hydro chromium lattice to the aero multiply crystal. The solid solution of hydrogen atom into aero X crystals reduce the thermic binding interaction, decrease the stability of the structure, and leading to high trade density fluctuations. And finally, the resistance of steel of hydrogen environment could be improved by lowering the proportion of hydrogen elements in steels, while the opportunity proportion of the very environments need to the further invested by means of the simulation. Okay, thank you.